What is going on, ladies and gentlemen? I go by the name of Gio. Welcome to my channel. In this video, I'm going to be going over what is Kafka. So, just to give a little backstory on what Kafka is, Kafka was created by LinkedIn. Yes, I'm talking about the professional networking site. I was surprised too. And it was outsourced back in 2011. Now, the thought process behind the idea of creating LinkedIn is they thought that there must be a fast, simple methods of transmitting information to people and applications that wish to consume it. You got to think about the needs of LinkedIn, right? LinkedIn is essentially a social media for professionals, and there's so many different events that are occurring within LinkedIn, from liking to sharing to sending people direct messages. Like, there's a lot of events that are going on and a lot of messages that are being transmitted. They needed a fast solution for that. Now, the reason that they made it is because they originally went around using traditional message brokers, and they had to set up so many different types of messaging brokers that to get the result that they wanted, they just thought it would be easier to create Kafka. And it was written in Scala and Java. So in this video, I'll be going over, first of all, what is Kafka and how it's being used in different ways that you can use it, and why it's being used so heavily even to this day. But before I can start going over what Kafka is, I thought it would be very important to give an intro on what is a messaging system to begin with. So that'll be the first thing that we'll talk about before we get into Kafka. So I think before understanding what Kafka is, you have to understand what is a messaging system. Well, a messaging system is responsible for transferring data from one application to another, so that application can just focusing on handling the data that is being sent over. So you got to think about it, right? Like I just said with LinkedIn has so many responsibilities, but other real world examples can include constant events that occur using any social media, right? For writes, for reads, for updating. You could think about the communication with the bank when you use your card, or when you transfer money using your app, and how those real-time transactions have to be consistent and on time. You could think about in IoT, or Internet of Things. If you don't know what IoT means, you can essentially think of how devices interact with servers. So you can think about like your refrigerator and how it connects to the Wi-Fi and pretty much communicates different events that occur. You can think about a robotic arm waiting for a stream of coordinates to move it properly. So these are different messages that occur, and messaging systems are used to transfer data from one application to another. And messages are queued asynchronously between the client application and the messaging system. So you have a client. So like I said, you could think of it as maybe there's an app, maybe there's a website, maybe there's a actual physical thing like a robotic arm, and you have a middleman or the messaging system that take in those events and pass it on to the next client. And the client can be a server, it can be another item, it can be anything that's want to communicate from the messaging system that the original client sent to the messaging system. So the messaging system is just a middleman. All right, so it takes in information and it outputs information based on whoever wants to consume from it. But all the messages are queued asynchronously between the client application and the messaging system. Now, there's two main types of messaging systems that I want to talk about before we really dive into Kafka, and let me go over them so you guys really understand. So the first one that we have is point-to-point messaging. It kind of seems pretty obvious based on its name, but in a point-to-point system, messages are persisted in a queue. As you can see in the middle, there's this little red little queue. It's a little bit blurry, sorry, kind of like had to increase the size a little bit, but you have a sender and you have a queue in the middle, and then you have a receiver. One or more consumers can, or which in this case is shown as a receiver because it's receiving the information, but another name for it is consumer because it's receiving or it's consuming the information from the queue. But a sender sends a message to the queue, and one or more consumers can consume from the queue. It can consume a particular message from the queue, right? But it's point to point, meaning it's one sender to one consumer, right? Yes, you can have many consumers connected to the queue, but only one consumer can consume that one message that was sent by the sender. So you can think of it like mail, right? You have a mailbox, you put the mail in the mailbox for a particular address, and with that mailbox, right, the person comes in and makes sure that that mail gets to that particular address, right? But only one particular address, not multiple addresses, right? So you have the sender and you have the receiver. That one person can consume it, but you could have many consumers that listens to the queue that can listen for specific events, right? Every house in the United States has the ability to receive mail, But just because they're connected to the mail system doesn't mean that they're going to receive all the mail. They're just going to have mail that is directly sent to them. So once a consumer reads or once a receiver reads from the queue, it disappears from the queue. So that is point-to-point messaging. The next one we have is the publish-subscribe messaging system, and this is really the more popular one. In a publish-subscribe system, messages are persisted to a topic, right? And unlike a point-to-point system, consumers can subscribe to one or more topic and consume all the messages in that topic. So in point-to-point, remember what I said, that a sender can send to a queue and it was restricted to be only consumed by one individual. Well, in the publish-subscribe, many individuals can connect to this queue and many individuals can consume from that queue as long as they ask for it. In the publish-subscribe system, message producers are called publishers, right? So the sender in this case would be called a publisher, and a message consumer are called subscribers. So that's why it's called publish subscribe, because you're publishing information to the topic, or in this case the queue, and then individuals that subscribe to the queue or to the topic will consume that information, right? It's like back in the day, I remember there used to be like a magazine for gamers, right? You'd go into your local GameStop and they will have magazines for gamers. Like you can subscribe to receive those magazines every month for 12 months, right? So all you have to do is subscribe to it and they'll send it every month, right? But as soon as you decide that you don't want to subscribe to that magazine anymore, you let them know, and now you don't receive any magazines anymore. It's very similar in this case, right? And in this case, you have the magazine company that sends information to the topic, or in this case the queue, and whoever subscribed to that topic or that queue will receive that information, or in this case the magazine, right? They'll receive that information until they're not subscribed to the topic/queue anymore. So what is Kafka? Because now we talked about messaging system, we talked about point-to-point, we talked about publish subscribe, but what exactly is Kafka? Well, Kafka is an open source distributed event streaming platform used by so many different companies for high performance data pipelines, streaming analytics, data integration, and mission critical applications. Because like I talked about, LinkedIn is used every day by professionals, and a lot of things go down in LinkedIn in regards to people applying for jobs. There's LinkedIn Learning, which provide tutorials on how to do certain things. So there's a lot of things that LinkedIn does, and with so many different events that are occurring on LinkedIn, Kafka is very, very important. But the fact that they made it open source means that a lot of people can use or leverage the power of Kafka, which is used as a data pipeline essentially. So Kafka is primarily used to build real-time streaming data pipelines and applications that adapt to the data streams. So you may have a series of events, but Kafka essentially works as the middleman to make sure that information is getting from point A to point B in a very fast, low latency way, and it handles a lot of real-time data feeds that occur. Because like I talked about initially, you have events such as banks who have different transactions that are occurring throughout the day, and you got to make sure that that is consistent. So as events are coming in through the pipeline, they're being handled by whoever consumes or subscribes to the information that are going through the pipeline. So Kafka combines messaging, storage, meaning that all the information that's coming through is making sure that it's stored properly, and it provides stream processing to allow for storage and analysis of the data that's coming through the pipeline. So a lot of this is going to make much more sense as I go through it and I break it down, but as a high overview, Kafka is just very great for building real-time data pipelines, and it has the ability to adapt to data that comes through that pipeline very quickly, and is able to handle it with ease. So the event-driven nature of Kafka, we talked about it, right? We talked about publish and subscribe, right? So with Kafka, you can send data as an event, and it's really just a message, right? Which are placed in things called topics. And just like how we saw in the publish subscribe photo, we saw that there's like a queue in the middle, right, that handles all the messages that are coming in, and on the other end you have a consumer that consumes information one by one through that queue. So in this case, a topic is essentially that, right? You have a subscriber that will consume messages from that topic, but then you have a publisher that publishes information or messages to that topic. So messages are published and consumers subscribe to consume that information that was published. And an event can entail these things, right? It can entail a key, a value, and a timestamp. And there's other optional headers that you can provide, but usually it's a key, a value, and a timestamp. And I gave a little example at the bottom. The key could be a name that you want to give, based on whoever's going to consume it. They can know what to do with that event based on the key, and then with that value, they can do some logic internally. So I want to give an example of when it comes to banking. So maybe you have a event where someone's withdrawing money. So you have the key name as withdraw, is a string called withdraw, and the value that the person want to withdraw is 500, and you know that the timestamp that the user is trying to withdraw that fund is July 4th, 2023 at 1 p.m. Maybe they're going to go buy some ice and some food for a barbecue that they're going to have later that day. It doesn't matter, but you just know that the event is going to be a withdraw, right? Because the key signifies it as a withdraw, and the value is going to be 500. So you know that, okay, say for instance, they're at a store, it publishes that information to a topic, a Kafka topic, and now the bank can consume that event, and it can handle that information downstream through other different servers and whatever they have to process that transaction. And that is the event-driven nature of Kafka. It's used every day. Like I said, it's a very powerful thing about Kafka. Even at my previous job, it was something that I've had to implement in various different ways. So that is one way, or that is the nature of Kafka in regards to the pub sub portion of it. So let's start talking about what is inside Kafka, right? And we're going to start off with the Kafka cluster. So a cluster is a computing concept which groups devices together to achieve a specific purpose. So in this case, a Kafka cluster includes multiple components, right? These components work together to create a reliable system. They work together to spread workloads efficiently across replicas and partitions, and that probably doesn't even make sense right now, but we're going to spread that out later on in this tutorial, especially partitions. The Kafka cluster make sure to manage the persistence and replication of data messages as they come through the system. If one broker, and we're going to talk about what a broker is, fails, then another Kafka broker steps in to offer similar services, so that it makes sure that there is no data loss or there is no latency issues. So the Kafka cluster just makes sure that there's a lot of components to make sure that information that comes through Kafka is safe and it's reliable and it's going through efficiently. Right, and there's many components that make sure, or that works together to make sure that happens, right? And that's really the whole purpose of the Kafka cluster. And I want to, show you guys what does this Kafka cluster entail. So what are the components within a Kafka cluster? So we have the broker, we have the controller, we have the partitions, we have the consumer, the producer, the topic, and I still want to talk about Zookeeper, even though it's being removed, and the Schema registry. So let's go step by step and discuss what each component does and the purpose within the cluster. So here's a little image on what a cluster entails. We just showed in the previous portion of the video that we have brokers, we have a producer that in the sense, like I said, produces a message. You have the consumer that consumes a message. You have the cluster that's in charge of all of it. It pretty much entails all the components, entails the broker, the producer, the consumer. We have the partitions, and we're going to talk about all of this. But this is just a high level view of what a cluster entails and what's inside of it. First, we'll talk about the Kafka Broker. It was the first in the list, so we can discuss that first. Well, a Kafka Broker is a single Kafka server. So within a cluster, we could have multiple brokers, but one Kafka Broker is a single Kafka server, and a Kafka Broker receives messages from the producer, which we'll talk about soon, but you can just think of the producer, as the name implies, as someone that produces or something that produces a message. And for each message that the producer produces or sends, it assigns a message offset and commits it to this storage. So a message offset essentially is an ID, because like I said, there's millions of messages that are going through or can go through a Kafka system. So we have to make sure that we have an understanding of what each message is and what it does. So an offset is given to a message so it knows its place within the Kafka system. Offsets are very critical for maintaining data consistency in the event that there is any failures or outages, or something crashes, because the consumer uses the offset to return the last message that it consumed after the failure. So in this case, you can think of it, or you can see that a producer, sends a message, it adds it onto the queue, and then it shows that it gives an offset of 6 to that message that was just produced. But we still have other messages that were in the queue. We have 0, 1, 2, 3, 4, and 5, and 6 was just added by the producer. But currently the consumer is reading from offset 5. Say for instance there was an issue while the consumer was reading from offset 4. Well, okay, that's fine because we still committed that offset to the storage. So now we know when we come back, we know that the consumer knew that it was at 4 because it was saved before it crashed. And now we can start reading from 4 and continue on to 5 and continue on to 6 until there is no more messages in the topic, right? So that's the important reason for, giving messages an offset, because first it makes each message unique, but now it shows where exactly the consumer can read from or consume the message from within the topic or the queue. So I shown in the original photo that a Kafka cluster can have many brokers, right? So a Kafka broker forms a cluster by directly or indirectly sharing information between each other. But in a Kafka cluster, only one broker serves as the controller, right? We can't have multiple controllers within a cluster. That could be a little bit confusing, because the controller is responsible for managing, the state of the partitions, which we'll talk about, and replicas. So the controller has a lot of admin tasks that it needs to handle internally, and having a lot of brokers do that will be an issue, or it can be confusing. So you have one broker that is responsible for handling the states of the partition, and like I said, we'll talk about that, and the replicas, and reassigning the partitions and registering handlers to listen and notify for any changes within the brokers. So that's a mouthful, and it's gonna make a lot more sense going in, as we start talking about the partitions soon. But just know that the controller is in charge of handling a lot of tasks internally, and usually one broker is assigned to be the controller. So I talked about topics a lot during this tutorial, but we actually never fully went over what a topic is. So here I am, right? A topic holds messages and events in a logical order and allows users to send and receive data from that topic, right? From the Kafka servers, right? So a topic can be split into multiple partitions, and I have another portion of the video that I want to go over to talk about partitions individually. But a topic is made up of, or can be made up of, multiple partitions, right? And a single topic can be scaled horizontally across various servers to deliver pretty great performance, well beyond the capabilities of just a single server. So what this means is that how we talked about how there's many brokers in a cluster, or there can be multiple brokers in a cluster, a topic can be spread out horizontally across all of those brokers. So instead of having a single topic for one broker, where if one broker goes down, all the information is lost, well, we can spread out that information throughout multiple brokers, so that information is scaled horizontally and we don't have to have a single point of failure. It can be spread out across many brokers. So here we have the anatomy of a topic. We have 3 partitions, and a partition is the smallest storage unit that holds a subset of records owned by the topic. So whenever a producer sends information to a topic, it can be sent to multiple units of partitions within the topic. So say for instance, in this case, there's 3 partitions. It'll be written to each one of those partitions. And like I said, if it's scaled horizontally, it'll mean that there's one partition in each broker. That can be partitions. Say for instance, there's 3 brokers. There can be partition 0 in one broker, partition 1 in another broker, partition 2 in another broker. Say for instance, the broker goes down that's holding partition 1. Well, that's okay because we still have partitions 0 and 2. And like I said, each message has a offset, so we can just start off, or we can just retrieve the offset that we need based on where the broker failed at. So we know, based on the controller, we know where to start off on because it has a record of where it failed. So that's the power of it, right? By scaling or by spreading the partitions across multiple brokers, a single topic can be scaled horizontally. It can provide performance far better than just having it on one single broker. And a single topic can be consumed by multiple consumers, right? So just how you see here where partition 1 has only 9 records compared to 0 and 2 that has all 12 records, a consumer can just start off retrieving information from partition 1 or it can later on pull from partition 0 if it need to, or partition 2, right? But right now it's just pulling from partition 1, so you can see that partition 1 has less than 0 and 2 because it's already being pulled from. Or maybe logically it only sent messages initially to 0 and 2, and maybe partition 1 is just getting the messages. So there's various things that can go on in regards to the anatomy of a topic. But a topic is very similar to a database or a folder, right? These topics can be divided into several partitions, and each partition can hold information that a producer writes from, and a consumer can retrieve from these partitions as well. And now we can start talking more in depth about partitions and Replica. In Kafka, a topic, like I said, is split into multiple partitions. Kafka writes records to each partition by appending the data. We saw how partition 0 in the previous portion started at 0 and it appends on all the way to 12. So it starts at a specific ID and it appends towards the end. So what gets retrieved from the topic is what was placed on first, right? If you guys have some coding background, it's like FIFO, first in, first out, right? Whatever goes in first is pulled out first. So all of the elements belonging to a particular topic are divided into and stored in these partitions. And like I said, they can be used to help scale the topic, because these partitions can be stored into different brokers. Just in case one broker fails, you still have that information in other brokers. And when a new message is written onto a topic, Kafka adds it to one of the topic's partitions. And there are various ways that messages are placed onto a partition, but if messages have the same key, they're published to the same partition. Kafka usually keeps more than one copy of the same partition across multiple brokers. This copy is called a replica, and if a broker fails, Kafka can still serve consumers with the replicas of the partitions that failed. So like I said, it's very fault tolerant, so if there is any issues, there are replicas of a partition, so that if there are any errors or if there are any faults, or if the broker shuts down when it wasn't intended to, well, there's some tolerance for that, and the information is replicated somewhere else to be retrieved from. So here's an example of a partition being spread out. So you have broker 101, broker 102, and broker 103. So you have partition 0 and 1, and they all belong to topic A, right? But you have partition 0 that's being stored in 101, but you also have a replica of it being stored in broker 102. So if, say for instance, broker 101 breaks, well, we still have that information in broker 102. And it's the same logic as if broker 102 fails and we need partition 1 and partition 0, well, we have another copy of it in broker 101 and in broker 103. So it's very fault tolerant, because if one broker fails, then another broker can pick up where it stopped. And speaking of writing, we have producers. Producers are client applications that publish or writes events to Kafka, right? So it can be many different types of clients. Say for instance, you have a client that logs information, right, and it sends it to Kafka. It can be that, or maybe you have an event that occurs, like I said before, with a banking institution that someone tried to do a withdrawal. That can be another event that's sent to Kafka. But all in all, a producer sends or publishes an event to Kafka, and that is stored in a topic where a consumer can then consume information. But usually the producer distributes messages across all partitions of a topic. So like I said before, there can be multiple partitions in various brokers, but the producer may direct a message to a particular partition in certain instances, right? So like I said, there's various ways that the logic handles putting information onto a partition, but that can be adjusted based on the setup of the cluster, right? On how you set up the broker and how you do the initial setup. There can be some logic that does it based on key, but it really is dependent on who sets it up, right? But usually it's great to spread the message across multiple partitions. Usually the producer should take care to distribute the keys evenly across partitions to avoid sending too much traffic to one single broker. So this even distribution is used in various of ways. You could also, if you have some coding experience and you know about sending requests like HTTP requests, you know that a lot of these cloud platforms like to distribute requests because you don't want one single line of failure. It's the same thing in real life, right? There's multiple Amazon trucks, there's multiple UPS trucks. You don't put all your mail in one truck, right? What if one truck breaks down, or a truck gets a flat tire? That means that day, individuals not getting their mail when they're supposed to, right? So you distribute mail based on sections, based on load, and you evenly try to distribute it so that everyone gets their mail on time, right? So it's the same logic with Kafka. You don't want to have, one broker dealing with all types of messages that are being published to Kafka. You want to make sure that it's distributed evenly, so that if there's 3 brokers and there's 100 messages, every broker is getting at least 33 messages. So if we produce, then I mean we have to consume, right? So we have the consumer. The consumers are applications or machines that subscribe to topics and process published data. So we just talked about the producer. When the producer sends a message to the broker or the Kafka topic, or is being stored in the Kafka topic, that means the consumer can consume that information off of the topic, right? So the consumer uses the offset ID, which we talked about with messages, that each message get the offset ID or a unique ID to make sure that we have track of that message, and it's also used to make sure that we didn't already consume, or the consumer didn't already consume that message, because we already have a log that we already consumed that specific offset ID, because the consumer stores the offset of the last consumed message for each partition so that it can stop and restart without losing its position. Because like I said, a broker can fail, right? And say for instance we already consumed that message and we're trying to connect to another broker, we want to make sure that we're at the proper position. So if we already consumed at a specific offset ID and we're connected to the replica partition that's stored in another broker, say for instance we stopped, or it broke at the offset of 10 and we need to get 11, we know that when we connect to the new broker with the offset ID, we don't need to consume 10 anymore. We can consume at 11 because we already have the log that shows that we consumed that individual offset ID. We can start at the next one. So a consumer interacts with a topic as a group, although a group can really consist of only one consumer if there's only one consumer, but it usually is a group of consumers, and that group is assigned a group ID. So the consumer group concept ensures that a message is only read by a single consumer in that group, right? So each consumer in that group is assigned a different partition, not the same partition. So let's take a look. So as you can see, we have a cluster and then we have 2 brokers, right? The first broker has a topic of P0 and P3, which is partition 0 and partition 3. And then we have another partition 1 and partition 2. But then we have 2 consumer groups. Like I said, a consumer group can have a single consumer, right? Or can have multiple consumers. In this case, there's group A that has 2 consumers, and there's group B that has 4 consumers, right? But each consumer in a group are assigned a different partition, but not the same partition. It's just to make sure that we're not consuming things that we're not supposed to, right? Each consumer is attached to a individual partition. So in this case of group B, C3 is assigned to P0, C4 is assigned to P3, C5 is assigned to P1, C6 is assigned to P2. Nobody's greedy. It's distributed evenly. Everybody gets its own piece of the pie. And in the case of group A, because there's not, a lot of group members within group A, each consumer gets 2 partitions, but they don't have to share from each partition, right? Each one of them get individual partitions. So in the case of C1, it gets P0 and P3 from server 1, but C2 doesn't even want anything from server 1 because C1 already has everything in server 1. So it's just going to get everything from server 2, which is P1 and P2. Everybody gets their own piece of the pie. It's all individual, it's all unique, right? Nobody has to share the piece. Now, if you're in a different group, then okay, you can grab from the same partition. But if you're in the same group, we got to make sure that everybody gets their own piece of the pie, or the information from the partition is not shared. Everybody get their own partition. And if there's multiple partitions and not enough people within the group, then all of that can be directed to that either that individual consumer, or each one of the consumers within that group gets a unique partition. So we talked about producers and consumers, and how a producer can send a message to Kafka Kafka Broker, and put it into the topic, and then the consumer retrieves information from that topic. But how exactly does the consumer knows the format at which the producer sent the message? Like how can we take that information and use it in the way that we need to? Like how does the consumer knows how it looks like, how it's structured? Well, we have the schema registry. So it's an application that resides outside of Kafka or outside of the cluster, and it handles the distribution of schemas to the producer and the consumer by storing a copy of the schema within its local cache. So the schema registry provides a central repository for managing and validating schemas for topic message data and for the serialization and deserialization of the data over the network. So as the producer sends serialized data to the topic, it would allow for the deserialization of that information over the network by the consumer. So the producers now know which topic received which form or which shape or which schema of the event, and the consumer knows how to interpret and extract that information from the events in the topic. So Kafka stores the schema, and now the consumer knows how to interpret and confirm that message. So with the schema registry, the producer, before sending the data to Kafka, talks to the registry, it communicates with the registry, and checks if that schema is already available, right? Did I already send a message previously with this same schema? Well, if it doesn't find that schema, then it registers that structure, and now the schema registry will cache that schema internally. So once the producer gets the schema, it will serialize that data from the schema, and it'll send it to Kafka in a binary format. And it'll be prepended with the ID of that schema, because each schema, like I said, has is cached and it's assigned ID, a unique ID. And then when the consumer processes this message, it will communicate with the registry or the schema registry, and it will use that ID it got from the producer and deserialize the same schema, right? And if the schema is a mismatch, then the schema registry will throw an error letting the producer know that it's breaking that contract, right? This is not the proper structure. So this saves a lot of time and headache when it comes to interpreting how a message is being sent and processed, because we now have the schema registry that saves information regarding the message. And there are different serialization types, right? So a producer can send a JSON type, a string type, a float type, an integer type, right? And that is being stored so that when the consumer receives that information, it knows, okay, this is going to be a JSON, right? This is a string, or this is a float or integer. Imagine if we didn't have the registry and now we just have to guess or assume what format that this message is going to be. That would be awful. So this registry keeps that clean and efficient. So let's look at this diagram, right? So you have the producer, right? It sends the schema to the registry, right? And then after that, it sends the information with the schema ID that it got from the registry and with the data, right? So then it's in this topic, and now the consumer can consume it with that schema ID and with the data, and now it can go and ask the registry, okay, I got this schema ID that was added with the data. Can you give me the schema that's associated to the data that was just placed into the topic, and so I know how to deserialize this information so I can understand what I'm gonna do with it in my application. And if it's proper, right, if it's a proper contract, then it will work fine and we're good to go. If not, then it's going to throw a pretty fat error, and you're not going to like that, and you're probably going to be really mad. But this is the flow, right? Full circle. And if the producer sends the information again, it's going to say, okay, does this schema matches what I already have within this schema registry? Because like I said, it's going to cache it, so we don't have to keep checking every time. We just got to check is the ID the same. And if it is, then we don't have to keep sending the schema. We could just continue on to this process of sending the schema ID and the data to the topic, and then the consumer will just try to destructure it based on the ID that's already in the schema registry. Now, if it's a new type of message, say for instance we change from a JSON to a string, well, that's a completely different type of message. So now we have to go in, send the schema again, get a new ID, send the ID with a cluster. The consumer's gonna be like, hold up, this is different. Let's go back to the registry. Let's see how to break that down. Okay, now I know this is a string now, and now I can put that string into whatever I'm gonna do with that string. Maybe it's a prompt, maybe it's hello world, I don't know, but we can do whatever we want with it from within the consumer. So Kafka and Zookeeper work together to run and complete Kafka Cluster, right? Zookeeper handles the leadership election of Kafka brokers. So we talked about how there's one broker that serves as the controller, and Zookeeper handles that leadership election of which broker is the leader, right? Is the controller. Zookeeper knows when a broker has either entered or exited the cluster. So if anything breaks or if anything was added on, it knows. So it knows when a broker dies. It knows who's going to be the new leader. If the broker was the leader that just died, it knows who to elect the new broker controller to be, and it knows how to hand off that topic partition pair too. It also keeps track when a topic is created or deleted from the cluster, and it maintains a list of different topics. Zookeeper is pretty powerful because it's also responsible for managing partitions, partition log pair leadership, handling replicas, in addition to performing general cluster housekeeping such as partition assignments and maintaining an in-sync replica list. And like I said, it does do the election of the broker on who's the controller, because remember, only one of the brokers can do it at a given time. You can have multiple brokers as a controller, so that's pretty important. I say all of this to say that Kafka is trying to move away from Zookeeper due to the reliance of all of this. Zookeeper in itself is its own individual software, right? Separate from Kafka, and that can be a problem in the sense that if Zookeeper breaks, then all of what I just said is useless, right? You have nobody to handle the election of the Kafka brokers. You won't have a way to know when a broker has entered or exited the cluster, or when a broker dies, how to give new leadership role to it, or who handles the partition. All of this stuff will be useless if Zookeeper shuts down, right? You have a single point of failure with Zookeeper. So that is the reason why Kafka is trying to move away from Zookeeper, right? It did its thing at its time, but now they're trying to move away from it. And they actually did create something that does exactly that, which is KIP 500, right? It is known as replace Zookeeper with a metadata quorum. So KIP introduces Kafka Raft, or KRaft for short, and it's essentially going to be a self-managed, or it is a self-managed metadata quorum, and it completely removes the necessity of Zookeeper to manage a Kafka cluster. And I know I read an article that said that it's already production ready, so like you could use it in production, and I'm pretty sure that as the new Kafka updates roll through, it already have it integrated in, but as of now I still think that there are applications still using Zookeeper and Kafka together, but just know that the name for the replacement is KIP 500. That would just have to be some research that has to be done based on your application needs. But the tutorial that I'm going to be creating using Spring Boot and Kafka is going to be utilizing Zookeeper. So you're still able to use Zookeeper as of now, but I'm pretty sure in the future this KIP 500, which removes the need for Zookeeper, will be the go-to. So then we have the Kafka API, right? We have an API for everything. We have the admin API, which enables you to manage and analyze Kafka topics, brokers, access control lists, and other objects. Then we have the producer API, which enables applications to submit or write data to streams to Kafka cluster topics. We talked about producer already. So if you want to write information to your Kafka topic, you can utilize the producer API. We have the consumer API, which enables programs to access or read data streams from topics in the Kafka cluster. So we talked about the consumer as well, which will allow us to consume information from the topic. Then we have the streams API, which provides stream processes that convert a data stream into an output stream, which will essentially, like I said, will allow us to output a stream that's within Kafka. And then we have the connect API, which create connections that continuously draw data from a source, and it will push that data into Kafka, into a targeted data system. So these are different APIs that Kafka has. So if you want to be an admin, if you want to see what's going on within your Kafka topic, brokers, you can use the admin API. We talked about the producer and consumers, but you can utilize an API to do the logic for that. If you're using streams, then you can use the streams API. And if you want to use the connect API to draw information from a source of data and push it into Kafka, then you can use the connect API. So what are the benefits of Kafka? Well, it's high throughput, right? Kafka can handle millions of messages per second, Like I said, the creators are LinkedIn, and LinkedIn is used by millions of individuals, and there's so many events that are going on. So that's the reason why it was so important for them to create it, because they needed a way to handle all the events that were occurring, but in an efficient manner. Then we have high scalability. We talked about the horizontal scaling nature of Kafka. So we can utilize that high scalability of Kafka to create many brokers and spread our information across those brokers to make sure that if one broker goes down, well, we already have a replica of it in another broker, so that information is available no matter what. Then we have the low latency nature of Kafka, which it can handle a lot of information, right? It can handle high volumes with low latency, as low as 2 milliseconds, right? It can handle things really quickly. Then we have permanent storage, database file systems that keep a permanent record of all the messages. Like I said, each message has an offset, but it also keeps a record of the message itself. So this is the storage capability of Kafka is pretty amazing as well. Then we have the high availability nature of Kafka. We can place clusters across multiple availability zones, whether you're in the US, whether you're in Japan. We can connect to clusters throughout many geographic regions, and it will be highly available. Then there's the use cases of Kafka, like who and why are we using Kafka? Well, we can use Kafka for metrics. If you're going to utilize you utilize it to monitor data that to create feeds for data coming through Kafka. Say for instance, you have information like say for instance numbers, like I said, banking, right? You want to see how much money went through the system July 4th, right? It was a big Independence Day celebration. How much money went through the system that day? Well, we can use that data that we got through the stream of data or that went through Kafka, and create a metrics logs for that, right? Or can create a metrics dashboard for it based on that information that went through the system. Then there's log aggregation, right? We can collect logs from various services, and it's all going through Kafka, right? And then we have the tracking activity, right? We can process large amounts of data to keep track of like clicks, or the amount of people that visited a page, or the user activity. That could all be done with Kafka. And then we have Internet of Things. Personally, that's one of my favorites, right? Or IoT for short. Kafka is used to stream data from devices to servers, and vice versa. So say for instance we have a robotic arm, we can utilize Kafka to stream that information to that robotic arm, so it knows to turn around and pick up this apple, right? All that information is being sent to the robots, or if you have any information that the robot sends back to your server, it can be done using Kafka. So these are just some of the use cases that Kafka can provide, and like I said, with the benefits that I said before, it can be done highly available, scalable, low latency. It's amazing. And then there's Kafka on the cloud. You can install Kafka in cloud computing environments such as AWS, right, which is pretty popular, and Azure, right. With AWS, for example, you can retain all the control that you need. You can set it up how you want to by installing Apache Kafka on Amazon EC2, right? So you can create a VM using AWS, and you can just install it, or install Kafka on that VM, and now you can set it up based on whatever you want it to, or how you want it to. And then if you use Azure, right, you can use Azure Event Hub, which allows you to utilize similar configurations that Kafka provides. All you got to do is provide an endpoint on Event Hub. And companies love Kafka, right? I think I don't have to speak too much about LinkedIn. LinkedIn is the originators of it, right? They created it, right? But then you have companies like PayPal, and you already know PayPal deals with a lot of events, especially monetary events. Then you have Netflix with a lot of streaming data. Kafka is used a lot. It just has the ability to handle a large number of diverse consumers, right? And Kafka can support low latency messages delivery, and gives guaranteed fault tolerance in the presence of machine failures. Because I talked about spreading information across different brokers, so knowing that it's safe even when things go wrong is amazing when it comes to these type of big companies, right? Because things can't go wrong, but it's companies like PayPal is utilized by a lot of people, especially in the business case. So yeah, you want to have confidence that when a fault does occur, there's a fallback. So Kafka is great for that. So what to take away from all of this, right? Well, Apache Kafka is open source. It's an open source stream processing software platform that helps deliver real-time data to applications. So if you're building if you're building an application that requires real-time data, then Kafka can be a product that you use. Kafka stores data durably and replicates partitions and replicates data to ensure that data is resilient to failures. So like I said, companies like PayPal and Netflix use it because it's very resilient, it's very fault tolerant, it's great at handling data. So you know that if it fails on one broker, then you have another broker that you can fall back on, or if you place it on multiple brokers, you can place it on 3, 4, 5, 6 brokers. You know that information is available for you in the case of it breaking on 3 or 4 brokers, right? We still have the 5th one. Consumers and producers interact with topics, and Kafka Streams provide stream processing. Kafka is comprised of brokers, controllers, partitions, consumers, producers, topics, and Zookeeper, which, like I said, is phasing out to using KIP 500, because, like I said, you don't want Zookeeper to be that single point of failure, because it is very important. It is doing a lot. So Kafka is making sure that they have their own internal thing that does exactly what Zookeeper does. So they are phasing out Zookeeper, but Kafka cluster is comprised of so many different things to make the whole thing flow. Like I said, the broker, controller, partition, consumer, producers, topics, all of this is working together to make a reliant product. Like I said, Kafka can be deployed on cloud services, right? Either with an EC2 instance, or you can even use Amazon managed streaming for Apache Kafka. And there are other cloud services like Azure, or if you like GCP, you can do that as well. So hope you found that helpful. Go ahead and subscribe. Click the bell icon for more. But there is another video that I'm going to be making utilizing Spring Boot, Java, and Kafka. We're going to create a service that will, we're going to create 2 services. You're going to have one service that acts as the producer and another one that acts as a consumer. And I think it'll be very helpful to digest all the information that you just learned. So you go ahead and subscribe and click the bell icon for more.